Hi, my name is Matt, and I'll be presenting the paper Scalable Coordination of Hierarchical Parallelism. This is some work that Vinay and I have done while working at NetApp to improve the performance of our commercial file system, which is called WAFL. WAFL is a high-performance commercial file system with its data structured as shown on this slide, with blocks within files and files within volumes, etc. A lot of previous literature has discussed WAFL in more detail. So when we were building a multiprocessor framework for the parallel execution of work within WAFL, we designed a data partition hierarchy based on the hierarchical arrangement of the underlying file system. Each data partition is associated with particular access permissions to data within the underlying file system, and the hierarchical arrangement of partitions implies that each one inherits the access permissions of its children. That is, data partition permissions are inherited up the tree. As work comes into the file system, it is mapped to one of the data partitions based on the data that it needs access to and the type of access it needs, such as read or write. In addition to the data partitions, there's also a scheduler that dynamically assigns data partitions to running threads in order to execute the operations queued up in each one of these data partitions. And it does so in such a way that ensures that any two concurrently assigned data partitions are safe to have their work executed in parallel. On this slide, we've shown an expanded view of the data partition hierarchy from the previous slide. What's important to note is that the hierarchical arrangement of data partitions implies that anytime one data partition is running, we must prevent the execution of all of its children and parent data partitions. This is analogous to a tree of reader-writer locks, where each data partition would be associated with a reader-writer lock, and executing the work from one partition implies taking the write lock of that partition as well as the read lock of all of its parents. And in fact, such systems have been implemented that way with a hierarchy of reader-writer locks, and those systems would also benefit from the techniques we present in this paper, although we more discuss things in the context of data partitions. Parallelism in this model is possible because work can map to different partitions that are along different branches of the hierarchy. For example, work can map to the volume logical data partition and the volume VBN data partition. And these are along different branches, and so the scheduler would be free to assign these two data partitions to different threads running in parallel. And so the work in each of those partitions would be executed in parallel on different CPUs. In contrast, the volume logical and volume data partitions are along the same branch of the hierarchy, and so the scheduler would not assign those to two concurrently running threads. To say that another way, work in volume and volume logical would then be serialized. So far in this talk, I've walked through some background on the hierarchical data and hierarchical data partitioning used in WAFL, as well as a little bit about how the scheduler ensures hierarchical exclusion of operations in the different data partitions. Now I'd like to walk through two problems that we ran into as we took this file system and ran it on more and more cores. The first problem I'd like to discuss is scheduler lock contention. Enforcing the hierarchical exclusion required by our data partitioning model requires that the scheduler have some sort of global knowledge about what other data partitions are currently running, so that when a new thread becomes available, it can assign a data partition to the new thread that is safe to run concurrently with the other currently executing data partitions. Historically, in WAFL, we have done that by providing a global lock around the data partition scheduler so that it could take the lock, look at the global state, and make a decision that was multiprocessor safe, and then release the lock. But on more cores, this lock became contended. In this graph below, I show the lock contention at increasing levels of load for a particular benchmark called SFS 2008 on a 36-core system. So what we see is at low load, the lock contention is quite low, but as load ramps up, lock contention increases significantly, up to a point where out of the 36 cores, 30% of all CPU cycles in the system are spent simply spinning on this scheduler lock. Beyond the peak, what you see here is as load continues to increase further, we get more amortization of data partition scheduling. There's more work in the system at higher load, and we get to run more operations for each data partition that gets scheduled. So in fact, the scheduler lock contention decreases past a certain point. In order to alleviate the lock contention that I presented on the previous slide, we divided the hierarchy of data partitions into a collection of sub-hierarchies, which we call scheduler pools. Each of these sub-hierarchies is associated with its own local scheduler. So now the problem of scheduling data partitions becomes two-level. First, we have to schedule the pools onto threads in such a way that the hierarchy is honored between pools, and then within each pool, the traditional scheduler is able to schedule data partitions. The advantage is that the scheduling of pools is much simpler than the scheduling of data partitions directly, and now the scheduling of data partitions only has to take the lock for the corresponding pool rather than taking the lock for the global scheduler. So in that way, the load on the lock gets distributed across many different scheduler pools. The scheduling of pools is itself a complicated issue that we delve into in the paper, but for here I'd just like to emphasize that it can be done without very much global synchronization and typically without any global synchronization between threads. As an example, consider that we assign the pool shown on the left called pool 1, 1 to some thread at runtime, and then another thread becomes runnable. It can be assigned any of the other pools at the leaf of the tree without requiring any synchronization, because any two pools that are at the leaves of the tree are safe to execute concurrently. And then those threads can call into the scheduler for each of the pools. It's also important to note that multiple threads can be assigned to a pool, and that's why it's required to subsequently take the lock for the individual pool to schedule data partitions to those threads. So in this slide we show the performance results using scheduler pools. So at the bottom I've shown in blue the same graph I showed earlier illustrating the lock contention at increasing levels of load on a 36 core system. Now in green I've also shown now the cumulative lock contention across the locks of all of the scheduler pools using the new architecture. And what we can see is that it maxes out around 1%, whereas the baseline with the global scheduler maxes out closer to 30%. So this scheduler pools architecture is effective at nearly eliminating lock contention on the scheduler lock. To evaluate how this reduced lock contention translates into improved performance, we looked at 3 benchmarks where lock contention was especially high with the global scheduler. We looked at SFS 2008, SPC1, and random write. And just using the scheduler pools architecture on a system with 36 cores, we were able to significantly improve both the throughput and reduce the latency of these 3 benchmarks. So the lock contention was significant in these 3 cases, and eliminating the lock contention successfully improved performance. The next problem I'd like to discuss is inefficient rescheduling of data partitions as we increase the number of cores in the system. The problem is that in order to schedule a new partition onto a thread, we have to stop all currently running data partitions that exclude it, that prevent it from running. This is analogous to a situation where you have multiple readers on a reader-writer lock running, and a writer wants to acquire the lock. Well, we have to drain all currently running readers in order to allow the writer to enter the critical section. And there's nothing that says they'll just all stop at the same time. So we have to coordinate that somehow. Historically in WAFL, what we've done is periodically draining all running partitions. The advantage of this is once all data partitions have been drained, we're free to run a completely new set of partitions, and anything is runnable at that point because there are no running data partitions. At the bottom here, I have a figure showing the problem with periodic complete draining. The blue bar shows some WAFL operation running on each core in a different data partition. And then after some timing interval, we decide to drain all running data partitions in order to reschedule the partitions. What happens is, since the WAFL operations don't have all the same runtime, some will finish earlier and some will finish later. So in that interim, after the first one finishes, but before the last one finishes, we cannot begin to run new data partitions. Instead, we have to wait until the last operation has completed. And this leads to a lot of idle cycles while we're waiting for drain to complete on all of the other CPUs. And the cumulative amount of draining that occurs in the system grows very quickly as the number of CPUs increases. In order to address the limitation presented on the previous slide where CPU cycles are wasted due to the periodic draining of all partitions in the system in order to perform complete rescheduling, we introduced a new technique called hierarchy-aware draining. This approach works by, in most phases of execution, simply trying to find some data partition that's safe to run at that time. And then at some point, we periodically decide to stage some data partition, which means set it aside to be executed next. At that point, we now have a mechanism for forcing the scheduling of that selected data partition. In particular, we leverage knowledge of the hierarchy to make effective use of all the CPUs in the system rather than sitting idle while we wait for everything to drain. In particular, once a data partition has been staged, we prevent the execution of any data partition that conflicts with the staged partition. However, any other partition in the system that doesn't conflict with that staged partition is safe to continue running. At the bottom of the slide, I've shown a figure to walk through a couple examples of how staging and hierarchy-aware draining work. So to begin with, we're going to pick a data partition to execute on each CPU. At some point, one of the partitions will finish running some amount of its work, and the core will need another partition to execute. At that time, let's say we've decided that a particular data partition, pool 1 for example, has waited long enough and needs to be staged to be forced in to run. However, it's not safe to run pool 1 at this point because it conflicts with partitions running on CPU 1 and CPU 2. So instead we simply stage pool 1. However, rather than sitting idle, waiting until pool 1 can run, CPU 0 now picks some other data partition that doesn't conflict with pool 1 so that it can make effective use of those cycles on that core. At some point, another partition will finish on another core and will need work to do. However, again, pool 1 cannot be scheduled because it conflicts with what's running on CPU 2. So we pick some other partition that is safe to run. Finally, on CPU 2, the last data partition that conflicts with the staged partition finishes running, and so the staged partition can be scheduled at that point. What we've achieved here is during this period of draining for pool 1, we've made a complete use of all of the cores rather than sitting idle while pool 1 was waiting to run. Especially given that on CPU 3, there's a long running data partition that runs much, much longer. So if we waited for complete draining, as we used to in the past, no core would be able to run any data partition until the partition on CPU 3 finished even. So all of this is making more effective use of the cores. At some point on CPU 2, this partition will finish, and we'll simply pick another data partition to run. So now we sort of go into the standard mode of just find something to run each time something finishes. Eventually we'll enter another time period where another data partition has been waiting long enough and we want to stage it. Let's say it's pool 0 in this case. Pool 0 is special because it's the partition at the root of the hierarchy, so it conflicts with every other partition in the system. So of course it can't run now while other cores are running anything. And there's nothing that CPU 0 can run that doesn't conflict with pool 0 because it's at the root. So it will sit idle. That happens again when CPU 3 finishes its partition again. And finally, the last data partition finishes and the stage partition can be run now. So here we did have significant wasted cycles during draining because we were scheduling a partition at the root of the hierarchy. Eventually this partition will finish, and now we're safe to run any partition on any core. So now let's take a look at the performance of hierarchy-aware draining in practice. But before we do that, let's look at this graph at the bottom of the slide, which shows a throughput versus latency graph for a random write benchmark on 36 cores at increasing levels of load. Traditionally, WAFL has used 2 milliseconds as the interval for its periodic draining. An alternative to hierarchy-aware draining is to increase this 2 millisecond period to 6 milliseconds, just so that we perform draining less frequently and therefore pay the wasted cycles cost less frequently. The 2 millisecond run is shown in blue, and the evaluation with 6 millisecond is shown in orange. And on this type of throughput versus latency graph, farther down and to the right is better. So we can see that up through around half of these levels of load, the 6 millisecond interval performs much better, that is with lower latency. However, at some point the latency spikes with 6 milliseconds, and this happens because we're waiting too long to run certain data partitions, and so their latency spikes. So at some point, performing draining more frequently actually improves latency and performance. In contrast, hierarchy-aware draining is now shown in the green dotted line on this graph. And this actually improves efficiency in the system at all levels of load. So it achieves the same performance as the 6 millisecond window where that's effective, but then it continues to provide those same improvements even beyond where the 6 millisecond draining sees a latency spike. In conclusion, in this talk, I've walked through 2 problems that we ran into while scaling the WAFL file system to more cores, and the 2 techniques that we used to address these limitations. The first was a technique called scheduler pools, which broke down our hierarchy of data partitions into a set of smaller, mostly independent schedulers that could perform this hierarchical exclusion without the requirement of large critical sections under a global scheduler lock. And we saw that this partitioning of things into subhierarchies significantly reduced lock contention and improved performance. The next technique was called hierarchy-aware draining, which allowed us to periodically reschedule the data partitions, but continue to make use of all of the cores as much as possible during the draining period while we are removing certain partitions from running. Both of the techniques that I presented today were implemented and evaluated in the context of the WAFL file system. However, we believe that both of these techniques would apply to other systems that are based on hierarchical parallelism, particularly those based on a hierarchy of reader-writer locks, which is very similar to the way the hierarchical parallelism works inside of WAFL. Thank you.